over 2.8 billion kilometers from the Sun, two vast and mysterious worlds patrol the outer reaches of the solar system. These are the huge icy bodies of Uranus and of Neptune, and they're unlike any of the other planets.
Tonight, The Sky at Night asks, why are these ice giants so unique?
Welcome to the Institute of Astronomy at the University of Cambridge, a place that played a key role in the story of the discovery of Neptune, the outermost planet of our solar system.
It's the perfect time of year to view Neptune and its neighbour Uranus in the night skies. So tonight we're dedicating this programme to them.
Coming up, we find out how the ice giants could provide clues to help us answer one of our greatest riddles.
Uranus and Neptune capture the very best of why we want to explore the outer solar system, and that is to try and understand why our solar system is so perfect for life to exist here on planet number 3.
Dr. Chamkor Garg reveals how their unique location makes the ice giants the exotic worlds they are.
By the time we're at the orbit of Uranus, the temperature is so low that it's not just water turning into ice. Complex gases like methane and ammonia are forming ice as well.
And Pete joins award-winning astrophotographer Damian Peach for tips on imaging the solar system's outermost planets.
First, the basics. Since Pluto has been relegated, Uranus and Neptune are the outer planets of the solar system. They are a colossal distance from the Sun, 19 times further than the Earth for Uranus, and a whopping 30 times for Neptune.
That distance means they take a long time to complete an orbit. 1 year on Neptune amounts to 165 Earth years. And it also means they're very cold. Parts of their atmospheres can reach temperatures as low as minus 200 degrees Celsius. Their most obvious feature, their striking colours, comes from thick atmospheres rich in methane that absorbs the red light but reflects green and blue.
Uranus and Neptune are clearly very different planets from the others in the solar system. So why are they like that? And what does it tell us about how the other planets were formed? Physicist Chamkor Garg is seeking the answers.
All the planets in the solar system are composed of unique combinations of chemicals. Whilst the gas giants are made almost entirely of hydrogen and helium, the same basic stuff of stars, Uranus and Neptune are chock full of methane and ammonia ice. And of course, these ice giants are completely different from the rocky inner planets like our own. So why do we see this variety? The answer to this question is all to do with heat. And to understand why, we have to go back in time to the birth of the solar system itself. Before we had planets, there was a huge cloud of gas and dust, known as a solar nebula. It was in the heart of this nebula that our star, the Sun, was born. But making a star didn't use up all of the gas and dust. The rest of the cloud continued to spin, flattening into a disk. Imagine this bench is our disk of stellar dust, all the bits and pieces that are going to go into making our brand new solar system. Now in the center, the Sun pushes the temperature up by over 1700 degrees Celsius. But as we move away, the temperature drops. And down towards the edge of this disk, an incredible 9 billion miles away, the temperature has dropped to a chilly minus 250 degrees Celsius. This temperature gradient, from inferno to freezer, is critical to the way each planet is formed. All elements and compounds have their own special properties, their own way of responding to certain environments. Take water. Cool it till it's very cold and it will form ice. But heat it up and it's going to vaporize into a gas. Now, all matter in the universe does this. And it's when it's solid, rather than liquid or gas, that it's most likely to become a building block for a planet, which is why the temperature gradient is so important. different elements change states at different temperatures. Now, here, close to the center of our primordial solar system, the temperature's upwards of 1,000 degrees Celsius. In this searing heat, only certain rocks and metals can remain solid, and that's why Mercury, Venus, Earth, and Mars are made up mostly of rocks and silicates.
Most rocky material has an extremely high melting point of 1,200 degrees Celsius. So, other than very close to the Sun, rock is solid throughout the solar system. And this explains why we find rock and metals in all planets, including the ice giants.
As we move further out into the solar system beyond Mars, we reach the snow line, an imaginary line where the temperatures drop to 0 degrees and water ice can form. Now, what's really interesting about this is that ice sticks together much more easily than rocks do.
And this explains why gas giants Jupiter and Saturn are a bit like these balloons, filled with hydrogen and helium. The ice helped the cores of these giant planets to form very early and suck up vast amounts of gas from the protoplanetary disk.
It's only when we get further out, much further out, double the distance from Earth to Saturn, that we start to see the ingredients of the ice giants appear. By the time we're at the orbit of Uranus, the temperature is so low that it's not just water turning into ice. Complex gases like methane and ammonia are forming ice as well. Suddenly, now that these volatile gases are locked into solid form, they can start to coalesce, and they seed what will become Uranus and Neptune.
These chemicals are what made Uranus and Neptune so iconic. They gave them their striking colour and drove their extraordinary weather systems. And as more and more of the volatile ice clumped together and mixed with frozen water, it formed a staggering 60% of the ice giant's mass.
But none of this could have happened without the deep freeze of the outer solar system. Any closer to the Sun, and these planets simply could not have formed.
And although the ice giants seem exotic to us, recent studies suggest they could be the most common type of planet in the galaxy. To find out why, I'm meeting Dr. Helen Fraser, who thinks a clue lies in one particular element within our ice giants.
The strange thing about Uranus and Neptune is they have 60 times more carbon in them than we see in the Sun. And that's very exciting because that's more carbon than we have on Earth, and it's certainly more carbon, 10 or 20 times more carbon than we have in Saturn or Jupiter. So it's a very big sort of warning beacon to tell us that the formation of Uranus and Neptune is somewhat different. And probably it comes down to the fact that Uranus and Neptune formed very close to what we call the CO snow line, the carbon monoxide snow line.
This is the point that carbon monoxide freezes, and that solid ice could have become a key building block for Uranus and Neptune. Scientists believed that this band of icy carbon monoxide might also exist elsewhere. And now, there's proof.
18 months ago, the ALMA telescope, which is a very big telescope in Chile, was used for the first time to image the carbon monoxide snow line in a protoplanetary disk outside our solar system, a different one, which is just forming planets.
And the evidence suggests that most planetary disks would also have carbon monoxide snow lines. So in each of these disks, there could be vast amounts of material to build ice giant type planets.
It's very likely, if we've got all these CO snow lines everywhere, that kind of process that formed Uranus and Neptune is absolutely the dominating process in other solar systems.
In which case, I guess it's very important for us to try and understand the formation of our own ice giants if we're going to understand what's going on out there with what seems to be most of the planets.
Absolutely vital, and they're big targets that we should really be sending probes to in the next few years and trying to get missions to.
In the last few decades, we've had enormous success sending probes out across the solar system to give us windows on new worlds. Cassini has been orbiting Saturn since 2004, and it's returned astonishing images of the ringed planet and its dynamic moons. Mars has 5 spacecraft orbiting it, giving us an unprecedented view of its varied and complex surface. And on the ground, 2 rovers leave no rock unturned. NASA's probe Juno is on its way to Jupiter right now, but the ice giants have been forgotten. It's been more than 25 years since Voyager 2 visited Uranus and then Neptune. But a group of scientists are trying to change that, planning a mission that will take us back to the ice giants. Maggie's been talking to Lee Fletcher to tell us why we should revisit these enigmatic worlds.
I think that we take the ice giants for granted. Why do you think they're of interest compared with the rest of the solar system?
Uranus and Neptune capture the very best of why we want to explore the outer solar system, and that is to try and understand why our solar system is so perfect for life to exist here on planet number 3. What makes the architecture of our solar system particularly special?
So if you do this mission, what would you expect to find?
Well, one of the big questions we're trying to address, so if you look at Uranus and Neptune, they formed at roughly the same sort of temperature. They took about the same length of time to form. You would expect them to be roughly the same sort of composition, the same sort of weather.
They look similar colours.
They have similar colours, and that's because of the amount of methane that they have in their atmospheres. Methane absorbs all of the red light, so what you're left with is the blue light to be reflected back at you. But there the similarities really end. In fact, Neptune, despite being the furthest planet from the Sun, is actually one of the most dynamic places in our solar system. It has these incredibly strong weather patterns and weather systems with clouds popping up and large cumulus systems developing that then get sheared apart by all the winds and jets. And these can happen on an hourly basis, so that Neptune really doesn't look the same each night that we look. Now contrast that with somewhere like Uranus. Uranus, when Voyager flew past in the 80s, was a very sluggish, very, dare I say, boring-looking planet.
Serene.
Very serene and calm, let's say that. All said and done, Neptune looks like a much more powerful, much more active planet than Uranus, despite being much, much further away, at 30 astronomical units from the Sun versus 20 astronomical units from the Sun.
Generally, we think of sort of the Sun powering weather, energy input from the Sun, sort of makes the turbulence, drives the weather. So, yeah, the further you're away from the Sun, you think the less dynamic it would be.
That would be the expectation. Most of the giant planets, if you were to look at them with infrared eyes, would be glowing hot.
So they're emitting
energy. Neptune has the biggest heat source of any of the giant planets, and maybe that's contributing to this really powerful weather that we see on that planet. But then contrast that with somewhere like Uranus. Uranus has almost no appreciable heat source that we can detect. Maybe all that energy is being locked away in the interior. Maybe it just can't get out through the various atmospheric layers. It can't convect and diffuse out to where we can see it. Or maybe there's just the energy is not there anymore. Maybe something in its distant past removed all of the energy from Uranus, which makes it a rather sluggish world today. Now, there's evidence to support that view.
That something happened.
That something happened, because one of the biggest mysteries about Uranus is why it's tilted over almost completely onto its side.
It sort of spins.
It spins that way as opposed to that way in our solar system.
That must make it very strange.
It's the oddball in our solar system. And the big question is, well, why has that happened, or how did that happen in the first place? And what implications does that have for how the planet itself works? One pole can spend 4 decades in the darkness of winter versus then 4 decades in summer sunshine, if you like. And that sets up a real difference in the amount of heating that each hemisphere gets. So maybe whatever caused that big tilt on Uranus, whatever bowled it over deep in its distant past after it formed, is the same explanation for why Uranus has no appreciable heat source anymore. It's all connected.
Now, going to both planets in one mission sounds pretty challenging. So which one would you go to?
That's a good question. We do have to choose between the two, and my choice would be to go to Uranus. And the reason for that is exactly what we said. It is the missing link, and it is the oddball of our solar system. There's nowhere else quite like it. Frankly, we need to do this to complete our picture of the solar system. The planets 1 to 6, if you like, out to Saturn, have now been characterized by orbital missions, okay? Uranus and Neptune have simply been forgotten about. That's the next step, in my opinion, in the exploration of our solar system. Let's get to those missing links.
Well, thanks very much, Lee. You put it over a pretty convincing argument. And good luck with the missions in the future.
Thanks very much. It's been a pleasure.
Neptune was the last planet in our solar system to be found. For good reason. It is by far the faintest of the major planets. To find it required an intellectual leap and an international space race. We've been joined by Carolyn Crawford, who's going to tell us this extraordinary story.
Ancient peoples knew about all the planets out to Saturn, but it wasn't until 1781, where William Herschel discovered the planet Uranus, that there was a realization that there were new planets out there just waiting to be found.
I suppose there's the things we can see with our visible eyes, and then beyond that, then we need other methods to detect them.
That's right, they're too far away, so they're dim and they're faint, and so any further progress really relied on having telescopes.
And Uranus was a surprise in the first place. Herschel wasn't out doing a systematic search for planets.
Yeah, and what a wonderful surprise it must have been to just discover the first new planet completely serendipitously when you're sweeping the sky with your telescope. But after that, people started observing Uranus and mapping out its orbit and how it was behaving. And that's where they really found a surprise, because Uranus wasn't moving as you might predict if it's just responding to the gravity of the sun and the other planets. Every so often it would kind of speed up, and then a little later it would slow down. And so by the 1820s, astronomers realized that maybe there was another planet out beyond Uranus, and the gravity was exerting a tug on Uranus every so often.
And this is where the Cambridge connection comes in.
That's right. So Neptune is peculiar in that it was the first planet whose presence was predicted, but it wasn't until a Cambridge undergraduate and then a graduate called John Couch Adams came along. He was the first one to tackle this problem properly and mathematically. He took a pot shot at where this extra planet would be, what it's, how far out from the sun, where it is relative to Uranus, predicted, what gravitational tug it would produce on that planet, and then compared that to what was seen in Uranus in the data. And then, obviously, he didn't get it right first time.
Because there's almost an infinite variety of possible planets.
You can move it further away, you can make it bigger, you can do a lot with it.
So you can imagine it took him a couple of years to refine his calculations. And by 1845, 1846, he's saying, okay, it's in that part of the sky.
And so it seems obvious. He's done 3 years' worth of work. You'd come down to this observatory, point the telescope at that position, and see what you could see.
Didn't quite happen that straightforwardly. And in practice, even though Couch Adams had started on this quite early, there was a French astronomer, Urbain Le Verrier, who was making the same predictions. And it wasn't until kind of midsummer 1846 when the Brits realised that there was a competing prediction that placed this new planet in the same part of the sky that they began to look for it in earnest.
So there's a race.
There's a race on. And so this is where this telescope came in. It was used for the search for Neptune here at Cambridge. And to find a new planet, you've got to map that whole area of sky from one day to the next, from 1 week to the next, and you're looking for the one object that moves relative to the backdrop of the stars.
There are plenty of difficulties. He couldn't point directly at one spot. The predictions aren't that precise. And, of course, no photography.
There's no photography, so all the observations are done by eye. And the astronomer who was leading the search, who was Professor James Challis, wasn't entirely sure whether he had seen it. Now, in practice, he had actually observed the planet. He did detect it, but he wasn't sure enough of his calculations. And in the end, he was pipped to the post by the French and the German astronomers.
So one way of describing this is the telescope that nearly discovered Neptune.
But it saw it, but it just didn't realise it.
Yes, it failed to find Neptune, I'm afraid.
Next up, Pete's guide to finding the ice giants and then getting the most out of observing them.
It's an excellent time of year for the outer planets of the solar system because both Uranus and Neptune are really well placed at the moment. And even from a light polluted location like a town or a city, they're both relatively easy to view. It's just possible to see Uranus as a faint dot with the naked eye. But with a bit of optical assistance, it's a much easier target. A small telescope really brings out the character of the planet because it has a striking emerald green colour, and it's worth taking the time just to look for that. It's a little trickier to spot Neptune, but don't let that put you off. Neptune is over 29 times further away from the Sun than we are, so that far out it's quite a dim planet, and it certainly can't be seen with just the naked eye. Now, with a small telescope, the view of Neptune shows that it has a character all of its own compared to its neighbour Uranus. It appears as a small disk, and its enchanting bluish colour really helps it stand out. Both planets do have more to offer, because with the right equipment, it is possible to make out subtle detail on their disks. I'm meeting award-winning amateur photographer Damian Peach, who's captured some striking images of these exotic worlds. So Damian, you're well known for taking some amazing pictures of the planets, including Uranus and Neptune. Have you got any top tips for getting the best pictures?
Firstly, you need a large aperture telescope, at least 10 inches aperture, to stand a chance of getting some detail on these planets. Secondly, I would say another important factor is that the use of filters, particularly near-infrared and red light filters.
Okay, so what's the purpose of the filters?
Now, what they do is to help contrast those brighter zones and darker bands much more clearly than you would otherwise see in visible light.
I've seen you've got some fantastic pictures on your laptop. Can we have a look at them?
Yeah, certainly.
Oh, wow, that's incredible. So that's Uranus, and the first thing that strikes me there is you've got colour in that shot. Is that colour that's been captured through the telescope, or is that added on afterwards?
The image you have here is actually the real image taken through a near-infrared filter, and it's been colorised later to give a more aesthetically pleasing appearance.
And that's because it's quite tricky to get the different colour components with it?
Exactly, that's right. Because these planets are so dim, it's very difficult to obtain good colour data to actually make a true colour image.
But it's worked really well. I mean, the detail there is amazing, because you've got these shaded bands running around the planet.
That's right, and one of the great things is it's only in recent times that it's become possible to start recording detail on planets such as Uranus and Neptune with amateur telescopes.
Okay. Why is that, do you think?
I think it's a combination of the development of very powerful software for processing the data that we're able to capture, and the cameras we have now are so much better than they were even 5 or 6 years ago.
Because these are pretty tiny. I mean, in terms of how they appear in the sky, they're not dissimilar to the moons of Jupiter. The moons of Jupiter are slightly smaller.
I mean, when you're looking at something like Neptune, it's only very slightly larger than Jupiter's moon Ganymede in apparent size.
That's incredible, isn't it?
So it's a very small object.
Have you got any shots of Neptune on there?
We have indeed, yeah.
Ah, there's Neptune and its moon, Triton. That's pretty amazing, because there is detail on that planet's disk, isn't there?
There is some vague markings visible, and again, this was taken through a near-infrared filter.
Absolutely incredible image. Really is something else. Thank you very much.
Thank you.
So no matter what your level of expertise, Uranus and Neptune are definitely well worth a look. So here's my guide to how to find them and some other highlights happening this month. Uranus is in Pisces, just south of the faint star Delta Piscium. To find Delta, first locate the Great Square of Pegasus, high in the southern part of the sky around 10 p.m. Extend the upper right to lower left diagonal of the square about half the distance again. Using binoculars, place Delta at the top of the field of view. Uranus is the lower of the two dimmer but similar brightness dots close to the centre. To find Neptune, first locate the pattern of stars which looks like a three-pronged steering wheel known as the water jar asterism. Look for the faint star Sigma Aquarii which lies south of the water jar. In binoculars, Neptune is the brightest dot to the right of Sigma. Finally, don't forget to keep a lookout for Orionid meteors which peak on the 21st of October. They appear to come from a region of sky above and left of Betelgeuse and Orion, and are the result of Earth passing through the debris stream of Comet Halley.
Uranus and Neptune don't make their slow procession across the night sky alone. Like many other planets, they have moons. Neptune's largest moon, Triton, is one of the most fascinating worlds in our solar system. Chris is speaking to Geraint Jones.
I guess the first thing to say about it is that it's big.
It is, yeah. So it's the 7th largest moon in our solar system. So it's smaller than our moon, slightly smaller than Jupiter's moon Europa, but bigger than Pluto, which until a few years ago was considered one of the major planets. And it's just got an incredible surface. So the one encounter we've had, Voyager 2 in 1989, that spacecraft revealed this amazing world, very young, very few impact craters, so it hasn't been exposed for very long. It's got an atmosphere and also active geysers on the surface.
And that, I think, is the iconic Triton discovery, Voyager actually saw those geysers shooting up into the sky.
That's right. If you look around the South Polar
Well, I
region...
think we can zoom in fact. Yeah, there we go.
So these dark streaks, the dark material is thought to be dust, maybe contaminated with methane, which is darker than the other ices on the surface. So they've been carried up into the atmosphere, and the larger particles fall down immediately downwind of the geysers.
So we get an eruption, and we get these almost dirty streaks following.
Exactly, yeah.
And now you said wind, which means there's an atmosphere. What do we know about the atmosphere of Triton?
Well, it's incredibly tenuous. So it's predominantly nitrogen gas. So it's thought that the pole that's being warmed the most by the sun is heated up. The nitrogen ice that's there sublimates, so it turns from a solid straight into a gas. It adds to the atmosphere. That material moves over to the night side of Triton where it's really cold, and it freezes out.
And its surface is incredibly varied. There's this South Pole terrain. There's also this other region up towards the top right of this picture where things look very different.
Yeah, so when that was first viewed in the Voyager images, the scientists almost immediately referred to it as the Cantaloupe terrain, and I've got the Cantaloupe melon here.
Very good. I'm glad we got to the melon.
Yes. So am I. If you look closely at the surface of this melon, you can see these interweaving features very similar to the fractures we see on the surface of Triton. It suggests that there's a liquid water layer somewhere under the surface. There's movement of the water ice crust, and through those cracks you get water lava breaking through, maybe mixed in with ammonia to make it more runny.
A water lava would be sort of a sludgy, nearly melted form of water, right? Because it's still very cold.
It is extremely cold. Liquid water flows out of the cracks and forms pairs of ridges on either side of these fractures. And this appears to have occurred over quite a large area of the surface mapped by Voyager 2. And if you look at some of the regions, you can see the hints of ancient impact craters that have been split in two by these fractures and have been shifted around.
So that means this activity is more recent than the impact craters.
Exactly,
so this is the kind of thing that Triton's possibly still doing today.
Yes, from looking at the number of impact craters, which show you how old the surface is, some parts may be as young as 5 or 6 million years old, which is incredibly young in geological terms, and may indicate that volcanism of the large scale type might be occurring even now.
That's it for this month. But if you want to find out more about ice giants or Pete's guide to how to find them, please go to our website at bbc.co.uk/skyatnight.
When we come back next month, we have a very special programme. We'll be following along as one of the most exciting missions of recent decades reaches its climax.
ESA's Rosetta probe will attempt to place a lander on comet Churyumov-Gerasimenko. The landing site has been selected, the timetable is in place, but it looks to be a daunting task.
We'll be at the heart of mission control for the landing itself, bringing you the first ever images from the surface of a comet and hopefully some early science from the lander's instruments.
So join us at 9 p.m. on the 16th of November. In the meanwhile, get outside and get looking up.
Good night.
We may all think the Americans won the space race with their moon landing in '69, but Russia's cosmonauts were spacewalking years before. A brand new film tells their thrilling and terrifying story tomorrow night at 9 here on BBC4.